Hey, this is Mr. Dahlstrom's pre-AP physics class. This is problem number 3 from worksheet number 2, training pulleys. We did the table problem in the first video. We did the hanging masses and incline pulley on the second problem. The last one we're going to look at here is the incline plane. Now the equation for this, or the setup, will be a little bit easier in some ways because we have two masses, so we'll only have two equations, but it'll be a little bit more complicated because we do have an incline plane here. Now, one of the things we have to realize here is that, and this is kind of a surprising fact that you can do, is that it would make sense that, you know, on our axes here, that would be positive y, and that would be positive x, just because that's how we've always done that. And you may be thinking, oh, I have to apply the same thing over here, but oh no, we taught, Mr. Dahlstrom said we should turn the axis. Can we turn this axis? And you can. Okay, so what it's going to look like for this, just as we've always done it, is that positive y is going to be perpendicular to the axis, and then positive x is going to be to the right, or as we say, the right over here, and that's going to be parallel to the axis. So you may be saying, Mr. Dahlstrom, didn't you say that we can't change our axis in a problem? You can't change your axis for an individual mass. One of the nicest things about pulleys here is that I've mentioned several times that pulleys don't change the tension, at least individual pulleys don't change the tension here, but they change the direction of the tension. This tension here is the same tension that is right there. So even though that's at an angle, basically you can think about the pulley, just realign them so that now you can use them. So we have to make sure we use up minus down for this axis, but then for over here we may need to do up minus down. So that means that's our y-axis, that's our x-axis, and so we'll go ahead and draw our traditional free body diagram we have for this. So there's f of g. We would have the normal force here. Now we don't have to use the normal force in our equation because there's no friction and normal force is not acting in the direction of motion. We do have tension here. We don't have friction, but we do have tension, which is this way. And we also have to make sure that we draw our triangle for this. So just like we practiced before we took the last test, this would be FG of y. And in this case, FG of y is not going to play into the equation because it's not horizontal to the direction of travel, or it's not parallel. So there, and then we have FG of x this way. And the angle provided is that angle right there. If you don't remember how to do inclined planes, free body diagrams, look back at the videos where we talked about that. And so that's the free body diagram for that. I guess I could have drew the thing around it, but I'll keep that off. And then this is this is M3 times G, and we've done that. 3 times 9.81 is 29.43 newtons. Okay, and that's our equation. So if we're looking at what really matters here, yes, both of these matter, up minus down, okay, in the direction of travel. And then the tension is going to matter, and then FGX is going to matter. And we also have to make a prediction which way these are going to go. Now, sometimes it's not always obvious with these problems because it can be somewhat ambiguous, but in this one I tried to make it fairly obvious that the 20 kilogram, even though it's on an incline plane, is so massive that it's going to cause an acceleration this way, which we've deemed as negative acceleration. Okay, and then this is going to be moving up, which we've deemed as positive acceleration. Okay, this is one of the whole reasons we don't call it AX and AY, because this would be negative A of X and that would be positive A of Y. But if they are the same acceleration in the system, which they are, then we can just realize that that number, magnitude, and that number are the same. Same thing as that tension and that tension there. Okay, so we'll write the equation here for the 20 kilogram mass. So M20 equals 20 kilograms. That is moving in the negative direction, so that's M times negative A. That's my work here. Okay. So right minus left, remember that this is right and this is left, so T minus FG of X equals M times negative A. Turn this here. Let me refocus this real quick. Okay, M times negative A, or negative 20A. And before I push everything over the other side, add everything, I'm going to go ahead and write it with this. This is f of g which is mg, but x, remember that the y is connected to the angle, so that's what gets cosine, but fgx is not connected, or it's, some might say it's opposite, and so that gets the sine of the theta, equals negative 20a, and we'll go ahead and plug in. So t minus mass is 20, times 9.81, times sine of the angle indicated up here, 40 degrees, equals negative 20a. I'll even solve for this here, so make sure, remind myself there. Go ahead and check it. 20 times 9.81 times sine of 40, get 126.11. I'll go ahead and go up to 3 decimal places here for this. 126.115 equals negative 20a. Then we're going to want to add this over to the other side, so t is equal to 126.115 minus 20a, and there's our equation. Okay, let's look at the mass 3 over here. I'll write it way over there. Is 3 kilograms, and this is going up, so it is m times positive a. This one should be pretty straightforward. T is up, minus 29.43. Oh, there's the light again. Let me get up and there we go. Back on. T minus 29.43 equals m times positive a, or 3a. And we'll go ahead and add 29.43 over there. The reason we keep seeing 29.43 is that when I was creating these problems, apparently I just couldn't be more creative than putting 3 down here for the mass. So that's why it's not a, oops, sorry. That should be 29.43 plus 3a. Right, and that's my equation. And the nice thing with 2 masses is that we have 2 equations, excuse me, with 2 tensions that are the same, 2 accelerations that also have the same magnitude, and so what we can do is just add the, or not add those, but substitute those, or just set them equal to each other. So kind of keep this over here and this over here. 126.115 minus 20a equals 29.43 plus 3a. I'm going to go ahead and add this over to that side, and I'm going to subtract this over here. So this becomes 23a. 126.115 minus 29.43. I'm rounding a little bit different. I'm just trying to be as accurate as I can here. 96.685, where the acceleration comes out to 4.204. Oh, of course, there you go. There's the bell. That's what it feels like to be here after school. Bells still go off. All right, so the acceleration, it doesn't come out as a negative number, which once again indicates that our prediction here was correct, that it is going in the negative direction, this is going in the positive direction. We can now plug these into here. And remember, there's only one tension here, so these numbers within rounding should come out pretty close. So I'm recalculating this from earlier today, so just double checking. This is 42.042. So this should come out within a few tenths at most. So 20 times 4.204. And I get, let me check this here, hold on. Make sure I entered it in right. 42.035. So we could see within 1/100th of a Newton. That is very, 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 very good, especially that we rounded there. So that's how you do that. We realize here it just goes back. If you can do if you know how to do a free body diagram, which a lot of you showed that you can do that on your Newton's Laws test, and I feel really proud because this is the first time I've ever had this as a problem where it's been mandatory that people solve and not an optional. So if you're looking at this and like, hey, I think I can understand this, what I would assign for you to do is to do number 4 on an own piece of paper. The acceleration here, if you want to check yourself, is 8.895 approximately meters per second squared. If you want to check, that's what it is. Once again, we're assuming that this goes down, and then, that this goes this way. Still saying that that is positive y, positive x, and then positive y, positive x. So if you can go ahead and solve that, and on your journey back to school, you'll be good to go. I'm basically creating a series of problems that will consist between the ones we did on Friday. But if you can do these problems, especially if you can do these problems, and I might add some friction problems and show you how to do them, they aren't necessarily more and more difficult there. So appreciate you checking in and staying up with the work, and I'm going to go ahead and sign off. Thanks a lot. Please subscribe.